Hi, welcome to Chapter 10, Part 3. This is our last video for Chapter 10 about gases, and we're going to talk about the deviation from ideal behavior, so real gases. So ideal versus real. According to the kinetic molecular theory, how do real gases differ from ideal gases? Well, real molecules have finite volume. If you remember in the kinetic molecular theory, it said that the volume of the gas particles can be ignored. But they actually do have a volume, and that affects some of their behaviors. And they do attract one another. They do have attractive forces, which we call intermolecular attractions. So they are attracted to each other. When do real gases most deviate from ideal gases? So if you have a real gas that is at a low pressure and a low temperature and a high pressure, it will deviate the most. So in the real world, the behavior of gases conform to the ideal gas equation only at high temperatures and low pressures. Okay, so a real gas behaves ideally at high temp and low pressure. Even the same gas will show wildly different behaviors under high pressure at different temperatures. And that can be shown here in this graph. If we assume we have 1 mole of a gas, and we use the ideal gas law, and we solve it for moles and rearrange it as such, so if we're forcing n to be 1, then this basically says that as we change the pressure, we should still have 1 mole of gas. So as we're changing the pressure down here, we should still have 1 mole of gas. So this dotted line here is the ideal. As you can see, these gases do not behave ideally, and their behavior varies. But in particular, at higher pressures, as you go up higher, the deviation from ideal becomes large, and it's different for every gases. Real gases don't behave ideally at high pressures. At lower pressures, they do behave ideally. Normally they say less than 10 atmospheres. So let's try to understand why there's this deviation from ideal behavior. So here we have 2 containers with a gas in it. This one is at a low pressure, and this one is at a high pressure. So you see at the low pressure, there's definitely more space between the particles. So if you were taking the whole volume of this container and the volume of just the particles, you'll see that the volume of the particles takes up a very small fraction of the total volume. But in this higher pressure example, the volume of the particles actually starts to take up a more significant fraction of the total volume, because now the total volume is smaller. So the assumptions made by the kinetic molecular theory, in particular where they say the volume of the gas molecules can be ignored, and there are no attraction forces between gas molecules, they start to break down at high pressure and low temperatures. At high pressure, the combined volume of the gas molecule is not so small that you can ignore it relative to the container. At high pressures, the gas volume tends to be slightly greater than those predicted by the ideal gas law. Okay? So because these particles have volume and it's a larger fraction of the total volume here, because the total volume is smaller, when you go and measure the pressure of your gases for the real gas, it will measure higher than what you would have gotten from ideal than what the ideal gas law predicts. And this is because the volume of the particles makes the total volume a little bit larger. So another reason for non-ideal behavior at high pressures is that there is attractive forces between the molecules. So if you're at a higher pressure, the molecules are closer to each other, and they are going to be attracted to each other. This attractive forces here is going to make this particle want to be attracted to this particle right here. This particle and this particle will be attracted to each other. So when it goes and hits the wall, it won't hit it as hard because it's getting pulled in the opposite direction. Therefore, when you measure the pressure, you're going to get a pressure that is less than that of the ideal. So let's look at this graph here. Okay. So you see here, you're getting pressures that are less than the ideal. And why are these less, this region right here? Because of the intermolecular forces are attracting the particles and they're hitting the wall less. So that is why you have less pressure here. But notice as you go to higher and higher pressures, you start to now exceed 1. So over here, you're higher than 1. So now the pressure is greater than what it should be. That's because at high enough pressures, the volume effect dominates, not the intermolecular force. Okay? So if you go to a high enough pressure, the volume effect will dominate this PV over RT ratio and tends to increase the pressure higher than the ideal. Okay? At low temperatures, though, your average kinetic energy of the gas is not energetic enough to overcome the intermolecular attractions. So if you have a lower temperature, notice this goes deeper here. At your lower temperatures, your intermolecular forces will be larger, just because the particles don't have enough kinetic energy to overcome it. What is happening as we heat the gas up? Notice that the deviation is going from being in the negative to actually being a little bit above it, because now it has enough kinetic energy to overcome the intermolecular forces. So therefore, at a high enough temperature, just your volume effect is going to dominate. So you're going to end up with pressures that are, or it's going to be higher than the predicted. So corrections for non-ideal gases. Okay, so the ideal gas equation can be adjusted to take into consideration these deviations from the ideal behavior. Remember, a real gas has a lower pressure due to intermolecular forces. So when we looked at the graph, remember it was lower than 1. And it will have a larger volume due to the finite value of the molecules. So we have to adjust for these. The pressure adjustment is due to the fact that the molecules are attracted and repel each other. Okay? Or intermolecular forces. The volume adjustment is due to the fact that the molecules occupy space of their own. Molecules have volume. So van der Waals came up with an equation that kind of adjusts for this, and it's known as the van der Waals equation. And here is the van der Waals equation. Okay, so the constants in the van der Waals equations, you have an A and a B thrown in here. The A is a measure of how strongly the gas molecules are attracted to one another. Okay, so this is related to your intermolecular forces. B is related to the volume or the size of your atom. Okay, so this term here, this n squared A over V squared, accounts for the attractive forces. It is added to the pressure since the attractive forces reduce the pressure. So it's added here to kind of compensate for that lower, when the ideal gas pressure measures higher than the real gas pressure. So you have to add this to the real pressure to adjust for it. The term NB accounts for the small but finite volume of the gas molecules. And it is subtracted from the volume so that you can move the volume downwards to where it's supposed to be. Because remember, the volume always measures a little bit higher for real gases because you have the volume of the particles into consideration. And over here, remember, the pressure always measures less than ideal because you have the attractive forces. So since the pressure measures less, you have to add this term that's related to the attractive forces. And since the volume measures higher for real gases, you have to subtract this term. And here are A and B. These are determined experimentally and measured, okay? And in general, A and B generally will increase with molecular mass. So large, more massive molecules have a larger volume and tend to have a greater intermolecular attractive forces. So they will deviate from ideal more than smaller molecules. So let's summarize. Gases deviate most from ideal when they are at low temperatures because they don't have enough kinetic energy to overcome the attractive forces. Gases deviate most from ideal when they are at higher pressure. When they are at higher pressure, the particles are closer together. So the attractive forces are stronger. And the volume of the molecules takes up a larger percentage of the volume because at higher pressures you tend to have smaller volumes. So the volume of the molecules are more significant. And when you have particles that have larger molar mass, when you have larger molar masses, your A and B constants in the van der Waals equation are larger, and they will deviate more from ideal. Mainly, too, the larger the atom, the more volume it takes up. Well, that is it for Chapter 10.